Hello, this is Kirtana and Aparna here to explain the BGP protocol. A routing protocol specifies how routers communicate with each other to exchange information that enables them to select routes between any two nodes on a computer network. Routing protocols are either of type interior routing protocol or exterior gateway protocol. We are conducting a simulation to better understand the BGP or the Border Gateway Protocol, which is an exterior protocol. BGP enables different autonomous systems to exchange information. The protocol is often classified as a path vector protocol, but is also sometimes classified as a distance vector routing protocol. In the distance vector routing approach, neighboring routers exchange routing tables that state the set or vector of known distances to other destinations. After exchange of this information, they use Bellman-Ford algorithm to find a better path. The difference is that in path vector routing, only the border routers communicate. EGPs are focused more on the type of information that can cross the border than on the path optimality. Here we see three autonomous systems 1, 2, and 3 which communicate by the BGP protocol. An autonomous system is loosely defined as a set of routers or networks that are technically administered by a single organization. Each autonomous system, AS1, 2, and 3, will advertise the networks reachable through them using the Border Gateway Protocol. A set of attributes of the route, like the sequence of AS, the next hop address, and the origin information are also sent. This is helpful to create policies.
BGP is a layer 4 protocol that sits on top of TCP, hence it is much simpler than OSPF. Now let us look at an example. Suppose your corporate network is connected to two internet service providers. To use BGP, you would need an AS number. Once BGP is enabled, your router will pull a list of internet routers from your BGP neighbors, who in this case will be your two ISPs. Then it will scrutinize them to find the route with the shortest AS path. An important aspect of BGP is that the AS path itself is an anti-loop mechanism. Generally, but not always, routers will choose the shortest path to an AS. BGP only knows about these paths based on the updates it receives. Unlike RIP, BGP does not broadcast its entire routing table. At boot, your peer will hand over its entire table. After that, everything relies on the updates received. Route updates are stored in a routing information base, RIB. An routing table will store only one route per destination, but the RIB usually contains multiple paths to a destination. It's up to the router to decide which routes will make it into the routing table, and therefore which paths will actually be used.
An interior gateway protocol is used for exchanging routing information between gateways or routers within an autonomous system. RIP and OSPF are well-known IGP protocols. Let us look at RIP. RIP uses hop count to determine the best path between two locations. Hop count is the number of routers the packet must go through till it reaches the destination network. The maximum allowable number of hops a packet can traverse in an IP network implementing RIP is 15. Hence, 16 hops is unreachable. In an RIP network, each router broadcasts its entire RIP table to its neighboring routers every 30 seconds. When a router receives a neighbor's RIP table, it uses the information provided to update its own routing table and then sends the updated table to its neighbors. The next is OSPF protocol. Open shortest path first is another IGP. It uses link state routing. The basic concept of link state routing is that every node constructs a map of the connectivity to the network. From this map, routing tables are derived using the Dijkstra's algorithm. Unlike RIP, where each router learns from its neighbors the distances, OSPF enables the router to learn the entire topology.
So now let's simulate a network using NETSim. For creating a simulation in NETSim, we go to Simulation, New and BGP Networks. We have various options in the NETSim environment. First, we create the given network. This network has 2 border routers, 2 internal routers, and 4 wired nodes. The wired nodes are the user end devices. After this, we link them using wired links. Now, to model the traffic, we create 2 applications. In the properties, we change the destination and the source IDs. In application 1, 5 is the source and 7 is the destination. We change the bytes per packet to 1472. Now we create a second application. Source is 6 and destination is 8. Again, we change the bytes per packet to 1472. Next, we set the properties of each device. Right-click and select Properties, first for the wires. We change the uplink speed and downlink speeds of each and change the bit error rates to 0 or no error. Now we change the properties of the border router. Both border router properties in application layer, we change the routing protocol to RIP. Similarly, we change the routing protocol of the router C and D to RIP. Now we run simulation.
We obtain the following performance metrics for the simulated network. The first are network metrics. Here we have parameters like simulation time, packets transmitted, packets eroded, packets collided, bytes transmitted, payload and overhead. These are measured for the entire network. Next are the link metrics. Here the packets transmitted and bytes transmitted for each link are given. There are 7 links in the given network. The next are queue metrics. Here there are some packets queued at every port. The number of queued packets and dequeued packets at every port for each device is given. There's also a column called drop packets, but here the number of drop packets are 0. The next are the TCP metrics and IP forwarding table. The protocol we used here is RIP protocol. Hence, we have 4 routing tables for the 4 routers. Router 1, router 2 and router 3 and router 4. The RIP routing table. Each router that implements RIP is assumed to have a routing table. This table has one entry for every destination that is reachable throughout the system operating RIP. The router ID. This is the unique ID of the router. The destination IP. This indicates the IP address of the host or network. The next hop IP is the first router along the route to the destination. The interface gives the number which indicates the physical network which must be used to reach the first router. The metric indicates the distance to the destination. The RIP table formation has three stages. The initial table. This table shows the direct connections made by each router. The intermediate table. This has the updates of the network in every update timer. Here we have set it to 30 seconds. The final table. The table that is formed when there is no update in the network. Next we have two BGP tables for the routers A and B, which are the border routers. In this table, the first column indicates the peer state. This can be idle or established. The idle state. This is the first state where the BGP waits for a start event. The start event occurs when someone configures a new BGP neighbor or when we reset an established BGP peering. It also starts listening for a connection in case a remote BGP neighbor tries to establish a connection. When successful, the BGP moves to the established state. The established state. The BGP neighbor adjacency is complete and the BGP routers will send update packets to exchange routing information. Every time we receive an update message, the whole time will be resetted. In case we receive a notification message, we will jump back to the idle state. Now let's look at the other columns of the table. The peer remote address. This indicates the remote IP address of the entry's BGP peer. The peer in and peer out updates indicate the number of BGP update messages received and transmitted in the correct connection. The peer in total messages and peer out total messages indicate the number of total messages received and transmitted to the remote peer in the current connection. The next hop is calculated with respect to the destination IP which has to be reached. This is shown in a figure. If the network to be reached is 11.3, then it has to go through the 11.3.1.2, which is taken as the next hop, and similarly the rows are filled.
We can play the animation to see how the packets move. The blue packets indicate the control and acknowledgement packets, and the green packets indicate the data packets. Next, we simulate the same network using the OSPF protocol. So, at each router, we need to change the properties and make the routing protocol as OSPF. Here, we set two parameters, that is the LS refresh time and max age. The maximum time between distinct originations of any particular link state advertisement is called the LS refresh time, and the maximum age that an LSA can attain is the max age. We set LS refresh time as 1800 and max age as 3600. Now we simulate the network again for 100 seconds.
Here, similar to RIP, we get the performance metrics. Let us look at the OSPF metrics. router 1, 2, 3 and 4 are given. Each router in the autonomous system originates one or more link state advertisement or LSA. A collection of these LSAs forms the link state database. The link state ID identifies the portion of the internet environment being described by the LSA. The router ID of the router that originated the LSA is the advertising router. The LS sequence number detects old or duplicate LSAs. Here we see the routing table. It consists of the destination IP and next hop IP as we explained before. The main difference between OSPF and RIP is that in OSPF, the router gains information from a large number of routers, while in RIP, it gets information only from the neighboring routers. Also, in RIP, there is a limitation on number of hops, which is 15, but in OSPF, there is no limit. These are the BGP tables. By performing the simulation, we understood the use of BGP and the method in which the BGP table is formed.